Hi and welcome to Unit 1, Topic 3, Video 4, and in this video we're going to look at two examples that require the use of proof by contrapositive. Now, what I really want to get through in these examples is, whilst contrapositive is theoretically challenging, solving and doing these examples actually procedurally is pretty easy. So let's have a look. Prove that for all n existing in the positive integers, if n squared is divisible by 3, then n is divisible by 3. Now, there is a chance here that we could do this by direct proof, but I'm going to move away from that. We're going to use contrapositive, and in the exam, you might be asked to use contrapositive. Now, obviously, why would we learn something where we could probably use direct proof in most cases? Well, there are some more complex examples where contrapositive becomes really important because the opposite of the implication is much easier. And you can kind of see it in this case. It's hard to start with the square and move to the original number. Whereas it's easy to start with the original number and then prove something about the square. So we're going to do that. I'm going to say that P is equal to n squared is divisible by 3, and that Q is equal to n is divisible by 3. And we're saying we want to prove that P implies Q. So what I'm going to do instead is I'm going to prove this is the contrapositive that not Q implies not P. And if I can prove that, then I've proven the original statement. So let's have a look. Firstly, not Q is equal to n is not divisible by 3, and not P is equal to n squared is not divisible by 3. So this is how we're going to do it. Now, it's going to seem like it takes a little bit longer, but actually it's the best way to go for this problem in terms of using contrapositive. It works out quite nicely. Basically, if n is not divisible by 3, and this goes along with our odd-even kind of concept, well then n equals 3 times some number, where m is also a positive integer. Remember, we talked about positive integers here. n is 3 times m plus 1, or n is 3 times m minus 1. Now you could do plus 2 as well, that would equally work, but I'll do plus 1 minus 1. So imagine we have 3m minus 1, and then the next number is 3m, and then the next number is 3m plus 1, and then we have 3m plus 2, and then we've got 3m plus 3, which is again divisible by 3. So we're going to use these two, either side of a number that's divisible by 3. So to get the number 9, we're dealing with the number 8 and number 10, either side. Okay, so I'm going to talk about case 1. And we've done cases before, and then I'm going to talk about case 2. So n equals 3m plus 1, and therefore n squared is equal to 3m plus 1 squared. I'm going to make the assumption that you're happy with expanding these types of perfect squares, and if not, then take a piece of paper and make sure you can. But I get 9m squared plus 6m plus 1, which is equal to 3 times 3m squared plus 2m plus 1, which is not equal to 3 times, for lack of a better one, a, where a exists in the positive integers, and therefore it's not divisible by 3. So it's worked for case 1. And in case 2, I'm going to have to move down a line, which is not as neat as I'd like, but it'll be okay. n equals 3m minus 1, n squared equals 3m minus 1 squared, which is equal to 9m squared minus 6m plus 1. And this is equal to 3 times 3m squared. I'm sure you can see where this is going now, plus 1. And that doesn't equal 3. I'll just reintroduce a new number here. I want to be careful not to imply that a can be two things at once. Doesn't equal 3b, where b is an integer, a positive integer, and therefore it's also not divisible by 3. They are the only two possible cases. If n is not divisible by 3, then n must be 1 less than a multiple of 3, or 1 more than a multiple of 3. But if I square either of those cases, I get an answer that's definitely not divisible by 3, and so therefore not Q does imply not P, and therefore P does imply Q as required, or QED. So that's example 3. Now let's have a look at a further example, and maybe you wish to pause it and have a go at this example first yourself. So this time, prove that if a squared minus 2a plus 7 is even, then a must be odd. So the counter proof to this, so this is my P, and this is my Q. The counter to this, or the contrapositive to this, is that not Q has to imply not P. And so therefore, we get, we start with not Q. Not Q is equal to A is even, and so therefore A is equal to 2n, where n exists in Z. So again, we're dealing with A's and N's and stuff like that. We introduce things as we go, and you'll see the same letters popping up a lot. As long as you're not double defining, it's all good. And my A is equal to some even now. Now, if A is equal to 2n, then hopefully you can see that A squared minus 2a plus 7 is equal to 2n squared minus 2 times 2n plus 7, which is equal to 4n squared minus 4n plus 7, which is equal to 4n squared minus 4n plus 6 plus 1, and that's equal to 2 times 2n squared minus 2n plus 3 plus 1. And if I let b equal 2n squared minus 2n plus 3, then I get that this is equal to 2b plus 1, which is odd, and therefore not p is true, because p is that a squared minus 2a plus 1 is even, but this is odd, so it's proving not p, and therefore not q has implied not p, and therefore p must imply q as required by the contrapositive statement. So there's a couple of examples. Definitely worth having a look at your textbook and some of those examples as well, and then having a play around with the exercise that's been set. All the best.